We would now like to begin the third session titled Pushing Frontiers of Natural Language. Is Deep Learning an Answer? The speaker, Professor Regina Barzilai, is from Massachusetts Institute of Technology. She is a recipient of a 2017 MacArthur Fellowship referred to as a Genius Grant. Now, ladies and gentlemen, please welcome Professor Barzilai.
Hey, wow, it's really weird to see myself like in the mirror. At any rate, I'm coming from Boston, so this is not one of the cities that the previous speaker was saying, like the top 1 or the top 10 or the top 100. But I'm jet lagged, so bear with me and participate so that I don't fall asleep during the talk. So, as you've seen, I changed the title of my talk, and it's called What Natural Language Processing Can Do For You. And before I start my talk, I want to ask you to raise your hand if you either studied natural language processing, doing research, or working in natural language processing, so that I can assess the audience. OK, we have some. So there are a piece of good news. So the talk is designed both for those who actually do natural language and those who don't. So there will be some part which will be kind of tutorial part, and there will be part which concerns the most recent research that we are doing at MIT on deep learning and natural language. So there will be something for everybody. But I can tell you, the question that I put in the talk, what NLP can actually do today, it's a real question for everybody, both for people who are new and who are trying in their business to think about what can they do with this technology, and even for people like myself. Like, for instance, yesterday when I was finalizing my talk, I went to Google. What happened here? Yeah. And, I just typed NLP, and what did I discover? All this wonderful thing about AI, which can predict your stocks, and about chatbots, which can save you 80 million in customer support. All these great, great things that I describe in the news. I discovered that, for instance, 99% of today's translation in the world is done by machines, which is kind of remarkable, correct? So a person, both a person who is in the field like myself and the person who is not in the field like yourselves, can kind of think, wow, we really have very, very intelligent machines. But if you continue doing some searches, even if you're not in the field, you can actually discover some really funny things. For instance, how many of you are familiar with the Hathaway phenomenon? OK, now you will be familiar. Next slide. So this was actually noted by a blogger who is not a scientist, that each time when Anne Hathaway, she's like this beautiful lady on the left, she's an actress, was in the movie or had some major news appearance, the stock of the Berkshire Hathaway, which is a major hedge fund in the United States, went up. And it was going on for a very long time. So the robotic trader not only was making mistake, it was making it for a very long time, nobody even discovered. Or maybe somebody did and didn't share. But this is just one example, maybe example that you are more familiar with. It's what happens with chatbots. Microsoft sent the first one, Ty, and it became racist. And afterward, they had another one, which called Zoe. Zoe also started to be anti-Muslim very soon after launch. A similar thing happened with the Tencent chatbots, which recently got shut down because they were criticizing Communist Party. And it's not like they really wanted to criticize it. They were just so naive and so much didn't understand what they are doing that they can easily got themselves into the territory where they're not supposed to go. So all these examples really demonstrate to us that natural language processing, the way we think about understanding, is nowhere close. But I want to share with you one slide that actually I borrowed from my colleague from Stanford, Professor Dan Jurafsky, where he describes how he at least sees natural language processing landscape. So what you see in the very left here in the column are the areas where, tasks which are solved, like spam detection, named entity extraction when you extract, organization, location. This stuff you can do perfectly well. They are done. They are very easy. There is nothing to think about. The second group is actually very interesting. The second group, when I was even a beginning faculty at MIT, was still only in the labs. And within the last 10 years, everything in that group got transitioned from the lab to industry. So today, as I said, machine translation is done mostly by machine. Sentiment analysis when you are trying to predict the sentiment of the review done by machines. So these technologies are not perfect, but they're good enough to be actually used and to give to somebody some utility out of them. The third group has the things which are still difficult, like dialogue systems, summarization, and others. So I actually very much disagree with this classification. And let me start by showing to you on the example of machine translation. So we know that machine translation does great things. As an illustration, yesterday I just went to one of the Japanese newspapers and I translated randomly one story. And to me, at least, the translation looks perfectly fine and logical. It's true that there are some mistakes, but I really didn't have any problem understanding the content of the message. And you can guys tell me if it looks okay to you, but I think it's reasonable, correct? Do we have somebody who speaks both? I guess many. So it seems reasonable, correct? Okay. Then I knew that one thing which Google does terrible is actually translation of recipes. I discovered it when I got a recipe in Finnish and I wanted to translate it. It was just ununderstandable. So yesterday I asked one of the Rakuten employees called Keiko to take a recipe from the Rakuten recipe website. This was, the beginning of this recipe. And this was a translation, round, again with a punch. Leading this kind of translation, it was funny, very funny, but you cannot cook with this thing. So here, what this example illustrates is that the same machine translation technology, because it is trained in a narrow news domain, it does news very well. It is not trained on recipes, and that's why it does this kind of funny things. So it's not the matter whether the technology is mature enough. Does it have narrow training data which enables it to learn? And in this case, it wasn't. And I'm sure that if we take, even in my class that I'm currently teaching, we build neural machine translation system, we train it in recipe, it will do a good job, but that's not currently what is in the production. Let's look at another task. I know that the last year the invited speaker was somebody from IBM, and he was talking about the wonders of IBM Watson. And we all were very excited. I'm saying we, people who, at least, in the US, everybody who were doing AI were, wow, this is really exciting. When we had Watson system beating humans in jeopardy, correct? And the winning question was the following. You can read it. I will read it aloud. William Wilkinson's An Account of the Principalities of Wallachia in Moldavia inspired this author's most famous novel. Now, for those of you who didn't read about Watson, how many of you know the answer to this question? None. I mean, really none. And to tell you, I was actually born in Moldavia. Really don't know the answer, okay? But, and of course, human couldn't do it, and machine could do it. Now, what can you do? You can just take this question, put it verbatim into Google, like as it is, and in one click, you're going to get the answer. So in this particular case, what enabled machine to solve it has nothing to do with intelligence. Its ability to cache huge amount of information and do fast retrieval. And if you want to see that, let's look at another task, which is called machine comprehension task. This is like a trivial task for, my son, when he could read, he could do it. This is a story, like a short story. Sally liked going outside. She put on her shoes. She went outside to work. And then there is a question, why did she put her shoes? So we all know why, because she went outside. Machine can solve this kind of task only with 71% accuracy. This is something that every human who can read can do with 100% accuracy. There is no tricky questions. It's not GRE. So the point here is that the tasks which are trivial for humans are really hard to do for the machine, because you really need to understand the text and know that when you walk outside, you need to put your shoes. So the point that I'm trying to illustrate here is machines can do stuff that humans cannot do. They can do it in volumes. But it doesn't necessarily mean that they understand the language the same way we do. And the smartness here in how we use natural language is actually in thinking what are the tasks in your job flow that you can delegate to machine to solve, and with its capacities and limitation, it will produce you useful output. And just to illustrate what actually traditional, standard NLP algorithm will do, I selected to show you a simple task which we do in collaboration with our Rakuten team from Boston. So here you can see Ankur, who is young. Where is Ankur now? Yeah, so this is Ankur and Pina. You see, they almost look like on the picture. Together with my students who are in Boston, in Cambridge. And the task is as follows. So in Rakuten, you can decide that you want to retrieve certain product. In this case, it's pink cotton blend shirts, whatever. So it does a good job. It retrieves all the shirts. Now, and the attributes shown here actually were specified by the person who is selling the shirts, correct? Now, the question is, if, let's say, our user wants to select some new attributes that the merchant didn't put, like let's say if it is waterproof or something else. So the task is to extract other attributes which are not specified by merchants to be able to do this retrieval, correct? Because if somebody asks waterproof, if it is you require waterproof, you don't want to show this shirt because it is not waterproof. So the specific and very simple NLP task here is to take a text and to predict a property from the text. Okay? So, and I'm using it as an illustration task because we can actually learn a lot about how NLP system works, looking even in this super simple task. Okay. So the way we are going to be solving this task is called supervised learning. You're going to be given documents. And for each document, instead of really giving the rules, how can I detect that this is the right property, what we're going to be doing is just adding the tag, -1 or +1. Is this product has a property or it doesn't? So as you can see here on a very intuitive level, what we're trying to avoid is a case where you need to specify the rules. That's what programmers are doing, you specify the rules. Here we're not going to be specifying the rules, we're going to be just saying, this is the output I want, and let machine learn the mapping. So how can machine do it? So this is a very standard specification. So here you have on one side training example, documents +1, -1, let's say, and at the end you get a new document, and there is a question mark. You need to predict. Now, of course, machine doesn't understand natural language, and it's not going to be reading the document and understanding it. You need to somehow take this document and translate it into a representation that machine understand. Now, I want you at this point to remember what I am saying, because when we talk about deep learning, we're going to be revisiting this point. The way people were doing before deep learning came into the game was the following. What they typically used is called like bag of words approach. You take a document and you translate it into a vector, which is just an array of numbers, in such a way that you record at every position whether the words in your vocabulary are present or absent. So for instance, you can say the first position would record whether the document has the word where. So for all the documents which have it, it's going to be 1. For all other documents, it's going to be 0. Does it make sense? So if you have, let's say, 10,000 the size of English vocabulary, this will be 10 size vector for each document. Most of the entries are going to be empty. It's going to be zeros. And there will be a few ones. So you can record the frequency. So what I did here, I told you, how to translate the document or something else into a vector. It was my design. And as I said, we'll come back to this point later. But I did this design, and now every document is just a vector with a label. And what machine has to do is to learn the mapping from one vector space to the labels. And if we would just have just two coordinates, what it means, I can actually visualize it for you. Now, every document is a point in this 2D space, which is with plus and the minus. And our task of predicting waterproof just means I need to find a separator. So I want all the pluses to be on one side and all the minuses on another side. Why it is a good thing? Because now, if you add a new document that we didn't know before what is it plus or minus, now our separator tells us. So tell me what it is. plus, correct? Because it's on the plus category. So this was all good, but some of you may be kind of feeling uncomfortable and saying, why did she decide to go for a line? Maybe these pluses and minuses are totally mixed up, and we don't need to have just a line, we can have something else. And indeed we could, and that's where we are getting to the land of deep learning. So let me just for a second forget our example, talk a bit about deep learning, and then we'll go back to this example. I don't know, there is like a weird echo. Do you hear it or it's only me? It's okay, I mean for you, because I feel that I repeat every sentence twice. Oh, sorry. Okay, thank you. Okay, so let's go to deep neural networks. So how many of you actually ever work with TensorFlow or worked with deep neural networks? Okay, roughly half. Okay, let me go fast through this part to get to more interesting stuff. So the neural networks originally were motivated by neurons in our brain, which are very simple computing units which take some input and generate you the output. They are very simple on their own, and you can see in this picture on is it left or right? Here on this picture, you can see that every simple one of this is just a very simple computing unit. You can see it can be one of these very simple linear separators. And then what you're actually doing, you are combining all these computing units together. Even each one of them is very weak. When you put them together, they can identify very complex patterns. And it's like an ant. Every ant is very weak, but as a colony, they're synchronized. They can do a lot of complex things. They're very parallel. They're organized in layers. And the reason we call them deep is because you actually have many, many layers. Okay, so they were known for decades, and you know all these recent explosions in computer vision, speech recognition, all comes to deep learning. And an interesting part is when this deep learning became popular, because when I was a PhD student, I was actively advised, don't even touch this topic. Because it was like a dead topic. If you want not to get an academic career, you would work on deep learning. At that time, on neural models. So the change happened in 2012. There is this big competition, which is called ImageNet, which has millions of images, and million images, and you need to categorize them in one of 1,000 categories. So for instance, this picture on the back, you should call it cherry, not a dog. What happened is, this is very interesting progression. In 2012, the first system that delivered best performance was from Toronto. It was the first deep learning system. You can see that it beat the rest of the system almost by twice. The mistake was 15.3%. But what was even more interesting, that the next year in the same competition, 15.3 was a tail performance. The next time, the best system was 11.7. Next year, we see the same behavior. The top system gives you the tail behavior, and the error gets to 6.6. This was a dramatic decrease in error. And you can see that the systems that were used were actually pretty complex. In order to make it work, you have to train 60 million parameters. And it was trained end-to-end to optimize the performance. So then when the whole AI community kind of saw the technology is ready. And the question is, are there any fundamental advices? And I know that some of you are not going to like what I'm going to say, but I would still say just because I'm a speaker, so I can. But you can argue with me during questions. I don't think that this success was due to really big fundamental advances. There were 4 things, in my opinion, that happened. First of all, there are lots and lots of data, and in the 80s was nowhere to be found. There was no even place to store it. The second point is that there were new computational resources and GPUs, which again were nowhere to be found. The third thing was actually something to do about our thinking about neural models. In the 80s, the thought was, let's just make very simple models work with very few layers, and then we're going to scale. And it turns out that it's much easier to train big models rather than to feed the very small models. And the final reason is the reason which makes it so easy for all of us to do deep learning, Because now what we have is a flexible Lego pieces. You don't need, if you want to build machine translation system, to start from scratch. You have real pieces and bits which encapsulate various functionality. You can just string them together and you're going to get your system. And I will show you in a second what I mean by it. Okay. So the reason in natural language processing, and now we are coming back to natural language, that these models were so welcome has to do with representation. You remember when I started talking to you how to take this waterproof document and translate it into a vector, I told you how to build this vector. I described it to you. And you would say, why did you build it this way? Maybe you should have built it another way. Maybe you should have done something else. You're right. I mean, we don't know. But here you can actually learn representation for both words, and these models, and I will show you in a second how, can combine the words and build representation for sentences, again, vectors, and then you can, with the same vectors, have images and even whole events. So you can easily talk about images, about sentences, about words, all in the same semantic space. And let me illustrate now how we can do this construction on a simple example. Let's say you have a description which say hardly suitable for rainy weather. For the models that I described you at the beginning, this would be a tricky sentence because it has the word rainy, which typically means waterproof, and the word hardly will be very far away. So the model which breaks it up to very short sequences would be unable to see the correlation. You cannot try to do all possible sparse n-grams. So this would be a tough example. So what the neural model will do, it will use this particular Lego piece. So this Lego piece, what it does, it will have some state, then it gets a new words, and it will move to a new state. So it's pretty similar to what you're doing now. You will remember what I've said until this point, then I say something else, and you're going to update your representation of what I'm saying. So specifically, you're going to start, like, let's say, with an empty vector. You see the word hardly, you update representation, then you get the word suitable, and so on and so forth. And at the end, you're going to get a vector which actually encapsulates the meaning of the whole sentence. And from that vector, you're going to predict the property. And you can say to yourself, how do you select this vector? The beauty of it, that the model actually would learn to do this process by assembling these Lego pieces in such a way that your prediction of the property is the best. So there is no me constructing this vector based on my heuristic. It's a model which actually learns how to represent this particular sentence. So, okay, let's talk about something more fun. So at this point, we kind of have some, at least, fundamentals of deep learning, and we can look and try to think what are the issues here and what is the research that should be done. The previous speaker before was telling us all this stuff. like we need to have, like, there is a jobs shortage in programming. And our models are so primitive, and that's what I want to illustrate you coming shortly. I can say at least people with AI background will have jobs for quite a number of years to come, unless Rakuten has some secret technology that I don't know about. Okay. So let's just look at it. So you look at this case, we're looking at these predictions of Rakuten, and we have 793 attributes. They range from, like, pajama type to the operating system type, lots and lots of them. So if you run a neural model on this data, you're going to get overall 89.9, which is actually a reasonable number. However, if you look at individual prediction, it varies greatly. For instance, some attribute called main stone you can do with 99.3%. If you look at cosmetic color, it's 62.4. And this is not the lowest. Now, can you guess what's so different about main stone versus cosmetic color? Sorry, can you speak up? In this particular case, actually, the main stone is not. There are several different types of the main stones. Let's just forget about if it's main stone or cosmetic color. You have two attributes. One seems to be doing, like, really, really well, and another one doesn't do very well. What will be, if you're doing data science, what will be your first hypothesis?
The dataset for Main-04 is really small.
Actually, for Main-04, the dataset is huge. It's 3.1 million for training. The test is the same size. The training is huge, so you can learn all different ways somebody can describe that Main-04. But cosmetic color, the set is much smaller. So in most of the cases, whenever you have small training data, this is really tough. And you can see that if we are looking at the most frequent attributes, you're doing very well. Whenever you're looking at less frequent attributes, you're not doing great. So the question is, how can you make deep learning model, which have millions and millions of parameters, do reasonable job when you don't have a lot of training data? And this will be always the case because, you know, we have Zipf-ian distribution, that there will be a lot of attributes which have small amount of data. So the idea here, and that's where a lot of research going on, is how can you do transfer learning? How can you borrow from attribute which is rich, where you have a lot of data, to the attributes which don't have a lot of data? You want to have this kind of democratizing behavior, okay? So clearly, you know, the first idea, we need to somehow capitalize on the similarity across the tasks. So for instance, let's say you have extraction of apparel material. There will be many other products which have nothing to do with shirts and which has nothing to do with apparel, which would be very similar in nature. For instance, in this case, you can have another attribute which is called jewelry material, which you would express in a very similar way. Sweatshirts made with a cotton blend, ring is made of 10K yellow gold. So you somehow, what you need to do, you need to divorce yourself from the traditional view of how machine learning is done, where you are training separately for each one of the tasks, and devise a model where you're learning representation in a smart way, in such a way that you're learning what is similar to what in hierarchical fashion, and you both share the representation and you share the weights themselves across those tasks. And that's exactly what we are doing with the Rakuten Boston team, learning this kind of both identifying automatically which tasks are similar and the ways to connect properly the weights. But now the question you will ask, what exactly does it mean, learning shareable representation? Like, I would now use something like totally distinct products which are really different, like blender and the lipstick, okay? And my goal is to learn representation, which would capture, for instance, which would help me to classify blenders, even though I've never seen any blenders. All my reviews, all my training is only about lipsticks. Like you have lipstick, you say how many stars the lipstick has. But I want to build a system which would know how to classify blenders. Does it sound reasonable? Like it should be, because none of you, even if none of you have read the reviews of blenders, you would be able to read it and to determine. So that's what we want to do with the system. Now, let's start with a very basic model. So if you just train your classifier to make prediction of the lipstick, on the lipstick, whatever label, most likely the representation, the vector you're going to learn, would somehow capture the meaning of the word, like in this case, best, favorite, battery, pamper, all these kind of things which are good to have in a lipstick, I guess. Now, the problem is, and that's why we're talking about transferable representation, what I want to do, I want my classifier not to use words which are only specific to lipsticks and never appear in blenders. I wanted to use the word like best, favorite, love, and other things which would be shareable while downgrading the words which are specific to one product. And if I manage to do that, then I can take a classifier that I only trained on lipstick and then take a representation of the document, a vector of blender, and I would be able to say the answer. But again, the problem here that now if I'm training something for blenders, I'm going to get one set of vectors. I'm going to train it on lipsticks. I'm going to get another set of vectors. And they're not going to be similar. So you cannot really apply a classifier because it all operates, let's say, in this green area. It really doesn't know how to process the blue points. So here the idea that comes is what you actually want to do is to take this representation when you are learning it and to modify it. You want to modify these vectors in such a way that you push blue and green points, vectors, different vectors, to be together in the space, to be unseparatable. Does this idea make sense? So you don't want, whenever you're learning representation, to have representation of two products be very different. You want to force them to be together, to be invariant of the product and only correlate with goodness and badness. So how can we do it? And the way we are going to be doing it is actually very intuitive. If I don't want to separate the blue and green points, it means I want to have an adversary. When I give to it a point, it should be unable to say what is its color. Here, you see, they're so together that it's impossible for me to separate and to draw the line. And that's exactly what the learning algorithm does. It optimizes two objectives at the same time. The first objective tells you you should be able to predict well based on your training data, correct? And this is this part. I would go here. So this is the first part. It just tells you you need to optimize well. And this part tells me whenever you build your representation, here sits your enemy. And whenever let's say it, whenever this enemy can detect whether it comes from Blender or lipsticks, you're losing the points. So this enemy forces you to find the representation which truly be shareable, but at the same time good enough to make the correct prediction. And in this framework, we very successfully were able to apply it to a variety of tasks, and you can see that it improved transfer both on attribute extraction task and on the sentiment task. And on the sentiment task is very interesting because what you see here, the yellow line is when you have a lot of in-domain data. This is the best you can do. In this case, it's 93%. If you don't do any transfer, you get 79. Just by doing the smart transfer, you happen to be exactly in the middle. So it shows to you if you're doing the smart algorithm, you can actually improve your performance. So this was the part about the transfer. And my group does now a lot of work in transfer. Because I think today, this whole view, we can just run the TensorFlow because we have huge amounts of training data and be happy and sleep at night, is a wrong view. Because even if you are operating within the same reviews, within the same subject, people change their opinion, the product get different features, the data always shifts. And we absolutely have to think nowadays, if we want to put these models into the practice, how we can deal with this constant change in the distribution, because our testing would never look the same way as our training does. So now I want to talk about another topic that is very dear to my heart. This is a topic about interpretability of neural networks. So Technology Review wrote recently an article about it. You see this green thing supposed to represent neural network. It's not a Halloween decoration. They call it the dark secret in the heart of AI. Whatever, this is like a romantic way to say interpretable neural networks. But the idea here is the following, that in many domains, whenever you need to do a prediction, you really need to know interpretation. And just to give you a very concrete example, there was some group from Germany that does, I think, loan approval with machine learning or some kind of financial task. And they're using linear prediction, and I asked them why. Because they seem like a smart people, so they definitely were aware that there are better alternatives. And they say because based on their laws, they have to provide justification if the loan was rejected. They need to say what was in the record of the customer preventing them from giving a loan, and they couldn't do it using neural networks because it doesn't directly attribute to specific site. So this was just one example. When you're doing, for instance, policy decisions, when you do clinical decisions, you really need to know interpretations. Okay, so we did, this is among the first papers, and actually the algorithm works very well. The code is available if you want to try. So there are many ways to define rationales, but I would give you one specific example. So let's say you have a review, and this is a beer review. There is a corpus when somebody, not us, collected, which has 1 million beer reviews, which are ranked in different aspects, for instance, look and aroma and taste and whatever. So you would say that the blue part is a rationale behind aroma being given 2 stars. Why? Because it says the aroma is kind of bubblegum-like and grainy. I guess it's a bad thing for those who drinks. So what we want to say here, we want the rationale to be sparse, meaning to be short. You don't want the whole document to be the rationale. You want it to be continuous, just to be a small portion and adjacent to each other. And you want it to be self-sufficient, which means that if I just show you the blue thing and you're, let's say, a beer drinker, you would know that it has to get 2 stars. For those of us who drink, I don't drink beer. For those of you who drink beer, would you agree that this is sufficient to give to it 2 stars? Is it because you disagree or because there is nobody who drinks beer? Or because you cannot say near your manager that you drink beer? Okay, at any rate, so for people, at least at MIT, they thought it's a good justification. And the point is that I don't want in my training to add a new thing to annotate, which is a rationale. I want to keep my training exactly the same. You have the task and the prediction, and the model needs to land the rationale in unsupervised fashion. So the way we're doing it, you can think about it in the following way. You take your beautiful neural model, which was taking the input and making you the prediction, building on the representation in the middle. Then you're going to break it up to 2 parts, really kind of turn it apart. The first part will look at the input and give you distribution over the rationales. That part tries to predict for me what can be a good rationale. It never sees the label, okay? Then there is another player which took the rationale that the first guy predicted and tries with that rationale to make prediction. You see what I'm saying? You kind of put a middleman where you have to select based on what you are given the prediction, and then you are making the prediction. And the interesting part is that you can say when they start, and you're training them jointly. They're trained jointly. So if the first guy really makes stupid decision, gives you really bad rationale, there is no way the second guy can do good predictions. So jointly together you train them. And see, I couldn't give the talk without having any formulas because I'm coming from MIT, so this is at least 1 slide with a formula. But this is a very intuitive formula. And what it says, that your general objective, what you're trying to optimize, Z is your rationale, Y is your label. So you want to say, I want it to have sufficient, that the loss between prediction on the rationale for label Y is small. I want to make sure that Z is very short, however I measure it. And then there is another part which takes coherence, where we have preference to adjacent pieces. So this is the objective. Because Z is not observed, you cannot directly train it, so you need to do something smarter. The expected cost here involves, exponential summation, so you can do a version of reinforced algorithm to solve it. But just to cut to the chase, you can see that it worked really beautifully in this data and in other cases. For this corpus, we had annotations of rationale that somebody else collected for thousands of reviews. And you can see that the rationale extracted by the model really match very well the rationales produced by humans. So I guess this was a good thing. And I can imagine that there are lots and lots of applications where this rationale can really help us understand why the predictions are done. And again, when we're looking at Amazon and we're looking at the score that people gave to a product, my first question is always, why did they give the score? Because we all have different reasons why we like and don't like something. So in this case, providing an opportunity to see why can be really, really crucial, and kind of summarizing the distribution over different reasons. So I believe there are a lot of opportunities here to do better. And right now, we're actually using this rationale. I have several students who work on it in a different way. What we want to do, we want today to train neural networks. Again, the previous speaker had these views that our job in the future is to take the machine and provide them training examples. Now, I can tell you, I cannot force one MIT student to do it. It's a boring, boring job. so in ideal case, we're not going to be annotating millions of examples. In ideal case, we will create an intelligent algorithm which can really cut dramatically the number of this example. And one way to do it is, instead of teaching machine like a monkey with millions and millions of annotation, you want to communicate with a machine in high level. The same way as when my son makes a mistake in his homework, I don't just correct it and let him learn himself to generalize. I explain to him why it is wrong. So one way we're currently using the rationales is to say, machine gives us the rationale. Human can correct the rationale, because machine learns something wrong, and then on this high level, you can retrain the machine without teaching it with millions of examples. So I think this whole way of rationalizing together with the machine can be a way to reduce the number of annotations. So now I am going to be going to my conclusion slides and deep years to come. So as you can see, there is a lot of activity in this area. It's very easy today to get into it. You can spend some time with your favorite neural package, and you can solve a lot of problems. And I would say today the success is determined in most cases by the availability of the training data which matches well the test that you're going to observe, and how tolerant the user is to the mistakes. So if you're doing machine translation, I don't read Japanese. Even if there are mistakes, this is the best I can get. There is utility for me. However, if you provide for me a model which does summarization of New York Times and it has mistakes, no way I'm going to use it. So this is an important consideration. And how to move beyond narrow task learning will be a big question in machine learning. How can we cut the amount of annotation and build models which can really intelligently generalize across the task, the same way as you can learn from one example because you have a background? How can you build this background into machines that it can learn from one example? And today, we have very highly functional solutions for many problems. It's still nowhere near true AI, but it doesn't mean we cannot benefit from it. So that's at least my conclusion. And this is my group. They did all the hard work. So thank you very much for listening.
Thank you very much, Professor Bartley. So,
Great talk, thank you. So I'm wondering, how interpretable are your transfer learning models? Do you know what transferred, what did not transfer? Do you know what the high order structures that you've learned that actually transferred?
So this is actually a great direction. So far, the two parts of transfer and interpretability didn't come together, but I definitely think we need to look into it. It's just for the reason that both are hard problems. We didn't put them together, but this is a really important one. And actually, thinking of it, one of the particular type of interpretability models that we're currently doing does something which is in spirit close to transfer. What it does, instead of like the rationales that I show you, explain to you per example. Now, it doesn't explain to you what are the general rules that the model learned, correct? It's just every example. So what we're doing now, we're building the neural model that learn a metric to cluster the example in such a way that every group of the examples can be explained by a very small, let's say, decision tree of limited length. So it pretty much kind of learns the domain with the associated rules for each subdomain. So you can think it as one step towards transfer, but we will definitely look into it. Great question. Thank you. Yes?
Hi, Salah. When you're using the transferable learning from transferring from it increased it decreased the error for the data with like smaller data set, right? But does it decrease the prediction for the other side, for the data that had the bigger
No.
Dataset?
At this point, it doesn't. And if you have 3 million training examples, most likely, you don't. Even if you look at the learning curve, at some point, you level off. Now, admittedly, we have a very crude way to say that, if you're really doing badly, we can improve. Even if you're doing okay, we still are not improving from extra data. But I would say that it's not, in principle, impossible. I would say we're just at the very beginning of developing this technology.
Thank you.
Yes.
So how well does your work generalize for things like word sense, right? Like, so how are you handling it? Domain adaptation will say word sense, because you have like something like bank, like a financial bank and a river bank, right? So it's typically like WordNet and those kinds of concepts. So are you learning embeddings that kind of handle context disambiguation?
So if you noticed, we actually, one way what you can do, you can just learn the embedding separately with one of the existing algorithms. And there is a work you can kind of attend to different senses and then use them. What we noticed in vast majority of our papers and our methods, that it works much better if you have data, not to do the pre-training, but just directly learn the embedding as part of your final task. So, and if for the part of your final task, it makes a difference, it would capture it on its own because it tries to optimize the objective. We don't explicitly model it. Thank you. Thank you very much.
Thank you very much.